Have you ever stopped to think what really happens when you type youtube.com into your browser? Within a fraction of a second, your device establishes a connection with a server that might be located thousands of miles away across oceans and continents and begins streaming high quality video to your screen. But how does this happen so seamlessly? How does your computer know which server to connect to, and more importantly, how does it find the address of that server? The answer lies in the fundamental system that powers the internet behind the scenes, called the domain name system. Every device connected to a network, whether it's a computer, smartphone, or server, must have a unique IP address to send and receive data. These IP addresses come in two forms: IPv4, the older, more widely used version but limited to about 4.3 billion unique addresses, and IPv6, a newer standard designed to overcome the address limitations of IPv4, offering a virtually limitless pool of unique addresses. However, humans aren't great at remembering strings of numbers. That's where DNS comes in. Just like a phone book translates names into phone numbers, DNS translates human readable domains like youtube.com into machine readable IP addresses. There are four key types of DNS servers involved in this process. The initial request from our computer goes to a server known as the recursive resolver. It's the front facing server which makes all the internal requests to other DNS servers on our behalf. Every recursive resolver is pre configured with a list of 13 root server IPs named a.rootservers.net to m.rootservers.net. These are not 13 individual machines, but each name corresponds to a globally distributed network of servers. Wait, why are these called name servers? These are specialized servers on the internet that help find the IP address behind the domain name by guiding your request to the right place in the DNS hierarchy. So, once a request is sent to one of the root name servers, it processes the request domain and based on the extension of that domain, like .com, .net, .org, it responds by directing the recursive resolver to a TLD name server. Root name servers store the information of TLD name servers extension wise, and based on the extension like .com, it will return the address of the top level domain name server. But what is a TLD name server and what does it contain? Top level domain name servers contain all the domain name details and their respective authoritative name server records. Now wait, what is this authoritative name server? If the TLD name servers have all the domain names listed in that particular top level domain, then why can't they just store all the IP addresses of these records and return them when needed? The number one issue here is scalability. There are millions of domains under TLDs like .com. If TLD servers had to store and update IP addresses for all of them, the data load would be massive. And any IP change which happens often to any of the .com domains would require updating the entire TLD server, which is a huge operational and performance bottleneck. And also, DNS is built on a delegated and distributed model, and it's not centralized. Hence, the responsibility of managing the IP addresses are delegated to the authoritative name servers, which are managed by domain owners or their DNS registrar like GoDaddy, Cloudflare, etc. This way, every domain can update its own records without touching the TLD infrastructure. So the TLD name server responds with the authoritative name server records. And lastly, the recursive resolver sends a query to the domain's name server. The IP address for youtube.com is then returned to the resolver from the name server. The DNS resolver then responds to the web server with the IP address of the domain requested initially. Then finally, the browser makes a HTTP request to the IP address, and the server at that IP returns the web page to be rendered in the browser. Now, let's take a closer look at how records are configured on an authoritative name server. Authoritative name servers hold different types of DNS records like A, Quad A, and CNAME. The A record stands for address and maps a domain name to its IPv4 address. This is the most basic and essential DNS record, and when a recursive resolver reaches the authoritative name server, this A record provides the final IP address. If a domain uses IPv6, the name server returns a Quad A record instead, which serves the same purpose but for IPv6 addresses. A CNAME or canonical name record maps one domain to another. For example, music.youtube.com can have a CNAME pointing to youtube.com. When a DNS lookup happens, it follows this pointer and resolves the IP address from youtube.com's A record. This setup is useful for subdomains because if the root domain's IP changes, you only need to update one A record. It's important to note that a CNAME doesn't force the alias domain to show the same content. It just points to the same IP, and the web server still serves different pages based on the original domain requested. But do you think it's practical to go through this entire multi step DNS resolution process involving several servers every single time you visit a website? No, right? And that's why DNS uses caching to make things faster. DNS data can be stored temporarily at different levels, and each stored record comes with something called a time to live or TTL. It tells the system how long the information should be kept, and the caching starts right from the browser. Modern browsers are designed to store DNS records for a short time so that if you visit the same website again, it can skip the whole lookup process and immediately use the saved IP address. If the browser doesn't have the record, your device checks with the operating system's built in DNS cache. This is still local to your machine and helps avoiding unnecessary network requests. If these caches come up empty, the DNS query finally leaves your device and goes to a recursive resolver typically run by your internet service provider. Even this resolver has its own cache and tries to answer your query from there. Only if all these caches fail does the resolver begin the full DNS lookup process by contacting the root name servers and working its way down. Now, let's look at a real example using the dig plus trace command and see how DNS resolution unfolds step by step. Once the command is executed, we can see a list of 13 root name servers written by a DNS resolver. The resolver that responds initially is usually the DNS server provided by your ISP or a public resolver like Google. And in this case, it has this IPv6 address. And since now we have the list of the root servers, the resolver sends a query to one of them. In this case, it's the eRoot server. It asks for information about the .com domain as we are trying to resolve youtube.com. The eRoot server responds with a list of 13 .com TLD name servers. The resolver then selects one of those, in our case the GTLD name server, and queries it for information about youtube.com. This server responds with the authoritative name servers for the youtube.com domain which belong to Google. Finally, the resolver sends a query to one of these authoritative servers, specifically ns4.google.com, and receives an A record. It's the IPv4 address of youtube.com. This IP address is then returned to the client that initiated the request, completing the DNS resolution process.